Hello there, and welcome to the Sleepy Space Channel. Almost everything we know about the Milky Way, we learned by looking along it, never up out of it. There are two directions we forget entirely: straight up out of the galaxy and straight down beneath it, toward the quiet poles where the band of stars thins away into the dark. Tonight we turn that way at last, and find that the space above and below is not empty at all, but quietly full. It holds the galaxy's oldest stars, swarms of suns older than the disk itself, whole small galaxies, and structures larger than almost anything in the bright plane. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. There is nothing above you or below you tonight that can reach you here. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. There is a direction we almost never look, and it is one of the two most important directions the galaxy has. Almost everything we have ever learned about the Milky Way, we learned by looking along it. On a dark night, far from any town, the galaxy appears as a pale band of light that wraps the whole sky in a circle. That band is the disk of the Milky Way, seen edge-on from a vantage point buried inside it. When we look toward the brightest part of the band, we are looking toward the crowded center. When we look the other way, toward the faintest part, we are looking out toward the rim. Both of those directions lie inside the flat plane of the galaxy. They are the directions of the disk, and they are the ones our eyes are drawn to. But a disk has two more directions, and they are the ones we forget. Straight up, out of the plane, and straight down, beneath it. These two directions point away from the bright band entirely, into the quiet and the dark, where the stars thin out and the sky seems almost empty. They are called the galactic poles, and they are the subject of this long, slow night. The question is simple to ask and unexpectedly large to answer. What sits directly above and directly below the Milky Way? Not the center, which has its own long story. Not the edge, which we have traced before. But the forgotten axis, the up and the down of the galaxy, the space that the bright disk seems to overlook. It is a strange thing to realize that this axis is always with us. Right now, one of the galactic poles is somewhere above the horizon, and the other is somewhere below your feet. We are embedded in the disk like a single speck suspended in a sheet of light, and the poles are simply the two quickest ways out of that sheet into the open space that surrounds the galaxy on both faces. The honest first answer is that the space above and below is not empty at all. It only looks that way from inside the bright plane. When the disk falls away beneath a rising point of view, what comes into sight is one of the most interesting parts of the whole galaxy. There are ancient stars up there, older than the disk itself. There are tight swarms of suns that formed in the galaxy's first chapters. There are entire small galaxies, circling slowly overhead and underfoot. There are long ribbons of torn-apart starlight and enormous bubbles of hot gas standing over the center, and slow clouds of gas raining back down toward the plane. All of this lives in the directions we rarely consider. The disk holds the youngest, brightest, busiest part of the galaxy, the part that makes new stars and draws the spiral arms. But the space above and below holds the oldest history and the largest, quietest structures the Milky Way contains. To look up out of the plane is to look back in time, toward the galaxy as it first was. There is also a symmetry in this that becomes, over the course of a night like this, its own kind of comfort. Whatever lies above the disk has a near mirror below it. The same old stars, the same swarms, the same faint reaching halo of gas. The galaxy is built evenly around its bright middle, and it has no real preference for one side or the other. That symmetry points towards something the title is quietly circling. The Milky Way has no true top and no true bottom. It floats in space with no up and no down of its own, the same in every direction away from its disk. We give the two poles names for convenience, but the galaxy itself does not lean either way. It simply turns, slowly, in the dark, holding us in the thin, bright layer where the light is. So tonight the path is a single, unhurried climb. We begin here, in the disk where we live, in the one layer crowded with stars. Then we rise out of it, slowly, passing through each thinning layer in turn, until the bright band falls away below, and the open space of the halo opens around us. We will see what waits there, and then we will understand that the same things wait on the other side as well. There is nothing in any of it that asks anything of us. The structures above and below are slow beyond imagining, turning on cycles of hundreds of millions of years, indifferent and patient. They were there long before us and will be there long after. For now, it is enough to let the bright band soften, to let the gaze tip gently upward, and to begin the slow rise out of the plane. It is worth asking why we so rarely look this way, when the directions are always available to us. Part of the reason is simply that the bright band draws the eye. The plane of the galaxy is where the stars crowd together, and a crowd of light naturally holds attention more than an empty stretch of sky. The poles, by contrast, look like nothing. They are the dark patches between the bright places, the parts of the night that seem to hold the least, and so the gaze slides past them toward the band, without ever pausing. There is also the matter of where we stand. Because we are buried inside the disk, the bright band surrounds us completely, wrapping the whole sky in a ring. It feels, from the inside, like the main event, the obvious shape of the galaxy. The poles are merely the 2 points where that ring is farthest away, and from inside the crowd it is hard to remember that those quiet points lead most directly out of it. The disk hides its own thinness by surrounding us with light. But the 2 quiet directions are there every night, one above and one below, no matter where on Earth a person stands. As the planet turns, the poles wheel slowly across the sky, but they never go away. At every moment, one of them is somewhere overhead and the other somewhere beneath our feet, marking the shortest paths out of the bright sheet we live in. To begin this night is simply to remember that those paths exist and to follow one of them slowly upward. There is a small thought experiment that makes the forgotten axis clear at once if one is careful with the word. Picture standing in a wide field at night, with the band of the Milky Way arching overhead. Everything bright in that band lies along the plane of the galaxy, and following it with the eye, in either direction, keeps the gaze inside the disk. To find the poles, the eye must leave the band entirely and turn toward the darkest, emptiest stretch of sky it can find. That dark stretch is the way out of the disk. Before the climb begins, it is worth being honest about a difficulty hidden inside the question. Space has no built-in, up or down. There is no floor beneath the galaxy for anything to rest on, and no ceiling above it for anything to hang from. Up and down are words we borrowed from a planet, where gravity pulls steadily in one direction and marks a clear floor below and an open sky above. The galaxy has no single pull like that, and so it has no natural up. When we say above and below the Milky Way, we are choosing a convention, and the choice is worth understanding. The disk of the galaxy gives us the geometry we need. A spinning coin, however thin, defines a flat circle, and the two directions exactly perpendicular to that circle are clear and unambiguous. The disk works the same way. It defines a flat plane, and the two directions straight out of that plane, one on each face, are the galactic poles. One is called the North Galactic Pole and the other the South Galactic Pole. The names are matched loosely to the familiar north and south of Earth's sky, but nothing about the galaxy itself prefers one over the other. Each pole points toward a particular patch of the night sky. The North Galactic Pole lies toward a faint, quiet constellation high overhead in the spring evenings of the Northern Hemisphere. The South Galactic Pole lies in the opposite direction, toward an equally quiet stretch of the southern sky. Neither patch holds anything dramatic to the unaided eye, and that emptiness is exactly the point. When the gaze turns toward a galactic pole, it is turned toward the least crowded line of sight the galaxy has to offer. The plane of the disk sits at a steep angle to the rest of our sky. This is why the band of the Milky Way does not lie flat along the horizon, but arches overhead at a slant, crossing from one side of the sky to the other. The tilt is a reminder that the galaxy's plane and our planet's daily turning have nothing to do with each other. We happen to live on a small world whose own axis points in its own direction, unrelated to the great flat sheet of stars we belong to. Astronomers built an entire system of measurement on this geometry. Rather than describing where a thing sits using the directions of Earth's sky, they describe it using the galaxy's own frame. They measure how far above or below the central plane a thing lies and which way around the great band it sits. In that frame, the disk becomes the natural equator of the galaxy, and the poles become its true up and down. It is a way of seeing the sky that sets aside our small planet and takes the galaxy itself as the reference. This is the geometry behind the whole question. Above and below are not mystical or poetic directions. They are simply out of the disk, toward the two poles, and almost everything we will visit tonight lives in the space those two arrows point toward. The old stars, the swarms, the companion galaxies, the bubbles, the falling gas, all of it stands above or below the bright plane, along this single forgotten axis. There is something quietly freeing in letting go of up and down altogether. We are used to a world with a firm floor and an open sky, and it can be difficult to picture a thing that has neither. But the galaxy genuinely has neither. It does not rest on anything, and it does not hang from anything. It floats, turning, with no orientation it would call correct. We could swap the names of the two poles tomorrow, and nothing in the galaxy would so much as shift. For the length of this night, then, the meaning is simple. Above means out of the bright plane in one direction, and below means out of it in the other, and the two are so alike that the difference hardly matters. With that settled, the bright band can begin to fall away. The climb out of the disk can start, gently, one thinning layer at a time, toward the open dark that waits along the axis we so rarely consider. The precise definition of the plane comes from the motion of the stars themselves. The disk turns, and the average direction of all that turning defines a flat sheet, the way the spin of a wheel defines the flat circle it traces. The poles are then fixed exactly perpendicular to that sheet, with no ambiguity. They are not chosen for convenience after the fact. They follow directly from the way the galaxy rotates, the one natural orientation the disk provides. What remains arbitrary is only which pole we call north. Here the choice was made to match the rough sense of Earth's own northern sky, so that the North Galactic Pole lies in the hemisphere we already called north. But the galaxy has no stake in this. The two poles are equals in every way that matters, and the labels could be swapped without changing a single fact about the structure they describe. The naming is ours. The geometry is the galaxies. This separation between our frame and the galaxies is worth sitting with for a moment. The north of our compass, the north of the night sky, and the north of the galaxy all point in completely different directions. They have nothing to do with one another. We live on a small tilted world inside a far larger tilted sheet, each turning on its own axis, and only by setting our own directions aside can we see the galaxy on its own terms, as a flat wheel with two poles of its own. It helps to remember that the plane of the galaxy was not always known to be a plane at all. For most of human history, the band of light in the sky was simply that, a band, with no understanding that it marked the edge-on view of a flat wheel of stars. Only by mapping where the stars lay in 3 dimensions did the flat shape of the disk become clear, and with it, the 2 directions standing perpendicular to it. The poles are a discovery, not an obvious feature, hidden in plain sight by our place inside the disk. Once the geometry is accepted, a quiet reversal follows. The bright band, which seems to be the galaxy, is really only its equator seen edge-on, the one slice we happen to lie within. The true extent of the galaxy, its halo and its reach, stands in the directions we cannot help ignoring. The most important parts of the structure are precisely the parts our eyes are least drawn to, which is part of why the up and down axis rewards a slow and deliberate look. To rise out of the disk, it helps first to feel how thin the disk truly is. We picture the Milky Way as a grand spiral, and seen face-on, it is enormous, a wheel of light roughly 100,000 light-years across. But seen edge-on, that same wheel is startlingly flat. If the galaxy were shrunk to the width of a dinner plate, the bright disk would be thinner than the plate itself, closer to a sheet of paper laid flat on a table. We live inside that sheet, far from its center, and nearly everything we ever see with the unaided eye is contained within it. The disk is not a single uniform slab, though. It has layers, and those layers are stacked in exactly the up and down direction this night is about. The youngest stars, and the cold gas from which new stars form, lie in the thinnest central layer of all, only a few hundred light-years from top to bottom. This is the bright, crisp plane where star formation happens, where the spiral arms are drawn, and where the dust gathers most thickly. Our sun sits within this thin layer, very close to its midline. Above and below that thin central layer lies a second puffier population of stars, fainter and older, called the thick disk. Its stars do not keep to tidy, level orbits. They ride on paths that carry them several thousand light-years above the plane and the same distance below, rising and falling as they circle the galaxy. The thick disk is the first hint of a pattern that will hold all the way out. The farther a thing sits from the central plane, the older it tends to be. To climb away from the midline is to move, gradually, into the galaxy's past. The cold gas and the dust keep closest of all to the plane. They form the thinnest layer, hugging the midline tightly, and it is this thin, dusty layer that blocks our view when we try to look along the disk toward the center. The youngest, hottest stars are born here, inside the densest clouds, and they light those clouds from within. Seen from far above, this central sheet would shine as the brightest, sharpest line in the whole galaxy, drawn in young blue stars and glowing gas. Our own position is almost exactly on the midline today. The sun lies so close to the central plane that the band of the Milky Way appears to cut our sky neatly in half, with roughly as much of the galaxy above the band as below it. This is no permanent arrangement, as a later part of the night will show. But for now, it places us in the thin, bright middle of everything, with the two poles standing equally far away in opposite directions. The layered structure of the disk matters for the whole journey, because it means that above and below do not arrive all at once. There is no wall at the edge of the disk, no surface to break through. Instead, a rising point of view passes first through the thin, bright layer of young stars and glowing gas, then up into the older, sparser, thick disk, where the stars are fewer and more aged, and then, without any clear boundary, out into the open realm beyond, where the disk itself becomes a distant, luminous sheet seen from outside. It is worth pausing on that gradual quality, because it shapes everything that follows. The galaxy does not end at a clean line. It thins. The stars grow older and more widely spaced as the climb continues. The gas grows fainter, and the bright plane recedes beneath a rising view until it hangs below like an island of light. There is no single moment of leaving, only a slow and steady fading, layer giving way to layer. So the picture to carry upward is this. We live in the thinnest, brightest, busiest sheet of the galaxy, a sheet far wider than it is tall, crowded with young stars and cold gas and dust. The thick disk lies just above and below it, older and dimmer. And beyond even that, the open space begins. With the disk understood as a thin, bright layer, rather than a solid floor, the climb can continue, up through the thinning stars, toward the first of the great structures that wait in the dark above the plane. The numbers behind the disk's thinness make the point more sharply. The thin layer of youngest stars and cold gas measures only a few hundred light-years from top to bottom, while the disk as a whole stretches 100,000 light-years across. The ratio is more extreme than a sheet of paper laid on a table, and yet this paper-thin layer is where nearly all the action of the galaxy happens. Everything bright and busy is pressed into the thinnest possible sheet. The reason the young material keeps so flat is the cold gas. Cold gas settles toward the midplane and pools there, the way still water finds its level, and it is from this pooled gas that new stars form. Because the stars are born in the flattest layer, the youngest stars are found closest to the plane, and the spiral arms, which trace where stars are forming now, are drawn in the thinnest sheet of all. Age and height go together, with the youngest things lying lowest and the oldest reaching highest. The disk is not perfectly flat either, though its gentle waviness changes nothing for us. Toward its outer edges, the plane lifts up on one side and dips down on the other in a slow, broad warp, as though the great record had been bent a little out of true. This warping is thought to come from the pull of the companion galaxies and the uneven flow of gas at the rim. Near the Sun, far from the edge, the disk is flat and steady, and the warp is something that belongs to the distant outskirts. A useful way to feel the thinness is to imagine traveling straight up out of the disk at the speed of light. Within a few thousand years, one would already have left the thin, bright layer of young stars behind. Within a few tens of thousands of years, the thick disk would thin away as well, and the bright plane would begin to fall behind as a luminous sheet. The crossing of the disk's thickness is quick compared with the enormous journey across its face, a reminder of how flat the Great Wheel truly is. The thinness also explains why our view of the galaxy is the shape it is. Living inside such a flat layer, we see the stars of the disk gathered into a narrow band, simply because we are looking the long way through a thin sheet. Were the disk much thicker, the band would be broader and softer, and the night sky would look quite different. The crisp line of the Milky Way is itself a direct sign of how flat the layer is that we live within. The first remarkable thing about the up and down directions is what they allow us to see. Within the plane of the disk, our view of the universe is choked with dust. The same thin, dusty layer that holds the spiral arms and feeds new stars also stands in our way, so that looking along the disk toward the center is like trying to see through a thick haze of smoke. The light of distant things is dimmed, reddened, and often blocked entirely. But looking up out of the plane, toward a galactic pole, the dust thins almost to nothing. The poles are the clearest windows the galaxy gives us. Because of this, the directions above and below the disk are where the wider universe comes into its sharpest view. A line of sight aimed at a galactic pole leaves the crowded disk quickly and passes out into open space, where distant galaxies appear in their countless thousands. There is very little of our own galaxy standing in the way, and so the view runs clean all the way out to galaxies so far off that their light has traveled for most of the age of the universe to reach us. This is not a small effect, and astronomers have used it deliberately. Many of the longest and most patient images ever made of the distant universe, the ones that gather faint galaxies by the thousands, were aimed at small patches of sky near the galactic poles. The reason is exactly this clearing of the dust. To look as far as possible into the universe, one looks out of the plane, through the open windows above or below, where our own galaxy draws back its curtain and lets the distance through. The opposite case is just as remarkable, and it draws the contrast sharply. Along the plane of the disk, the dust grows so thick that it hides whole sections of the universe beyond. There is a band that circles our entire sky, following the bright line of the Milky Way, where almost no external galaxies can be seen at all. They are not missing. They are there, in their usual numbers, but the dust of our own galaxy stands between us and them and draws a curtain across the view. The galaxies behind that band are among the hardest in all the sky to study. So the two directions could hardly behave more differently. Turn to face along the bright band, and the universe closes, hidden behind stars and dust. Tip the gaze toward a pole, and the universe opens, galaxy after galaxy, emerging from the dark. The same sky holds both the most blocked and the most open lines of sight we have, and the difference between them is simply whether one looks along the disk or out of it. This gives the up and down axis a second character, beyond holding the galaxy's oldest contents. The poles are also our best view of everything outside the Milky Way. To understand our place among the other galaxies, to map the great structures of the universe, to look back toward the early cosmos, we look through the windows above and below. The forgotten axis turns out to be the one that connects us most clearly to the universe at large. There is a quiet irony worth noticing here. The part of the sky we find least interesting to look at, the dark and apparently empty patches near the poles, is the part that opens onto the most. The bright band that draws every eye is in fact the most closed-off direction we have. What looks full is, for the universe beyond, nearly opaque, and what looks empty is the clearest possible view. It is a fitting way to begin the climb in earnest. The poles are the galaxy's open skylights, and through them, on a clear enough instrument, the whole observable universe is laid out in the dark. With that in mind, the rising view can turn from what lies beyond the galaxy back to what lies just above it, to the first great structure encountered on the way up, the old and quiet halo of stars that surrounds the disk on every side. The band where galaxies disappear has a long history of hiding things from us. For a long time, whole galaxies lying directly behind the plane went unseen, simply because the dust stood in the way. Only by looking in kinds of light that pass through dust more easily have some of these hidden galaxies been found, lurking behind the bright band, where the ordinary view shows nothing. The plane keeps secrets that the poles would have revealed at once. The dust does not only block light, it reddens it. As starlight passes through the dusty plane, the dust scatters away the bluer light more than the redder light, so that distant objects seen through the disk appear dimmer and redder than they truly are. Looking out through a pole avoids this almost entirely. The light comes through clean and true, neither dimmed nor reddened, which is part of why the poles are so prized for studying the faint and the far. The clearest windows have shaped how we map the universe. Surveys that count galaxies across the sky lean heavily on the regions away from the plane, where the counting is honest and little is hidden. The great three-dimensional maps of how galaxies are arranged, the maps that revealed the strands and hollows of the cosmic web, were built largely from the open windows above and below the disk. What we know of the universe's large-scale shape, we owe in part to these quiet, dust-free directions. Even the clear windows are not perfectly empty, and the thin haze that remains has its own quiet beauty. High above the plane, far from the thick dust of the disk, faint wisps of dust still drift, lit softly by the combined light of all the galaxy's stars. These pale, ghostly veils are the thinnest remnants of the galaxy reaching toward its poles, and they must be carefully accounted for when studying the faint universe beyond. Even our clearest windows are draped with the most delicate of curtains. There is a fitting symmetry in the fact that the emptiest-looking parts of our sky open onto the fullest view of the universe. The bright band that seems to hold everything is, for anything beyond the galaxy, nearly a wall. The dark patches that seem to hold nothing are, in truth, our great open windows onto the cosmos. To understand our place among the galaxies, we look not at the crowded plane, but at the quiet poles. The contrast between the two directions is so reliable that it has become a working tool. When astronomers wish to study the faint and distant universe, they choose fields of view well away from the plane, knowing the dust will be thin there. When they wish to study our own galaxy's disk, they look along the band. The same sky serves both purposes, depending only on whether one looks out of the plane or along it, and the quiet poles have become the preferred windows for nearly everything beyond the Milky Way. Rise above the thick disk, and the galaxy changes character entirely. The orderly, rotating sheet of stars gives way to something far older and far quieter. Surrounding the whole disk, above it and below it, and out to every side, is a great rounded cloud of ancient stars, scattered thinly through an enormous volume of space. This is the stellar halo. It is the oldest visible part of the Milky Way, and it wraps the bright disk like a faint spherical shell of old light. The stars of the halo are nothing like the Sun. They are among the first generations of stars the galaxy ever made, formed in its earliest chapters, before most of the heavier elements existed. Because they were born so early, they are poor in those elements, built almost entirely from the simplest material the universe began with. They are the chemical record of a younger galaxy, still shining, still circling, long after the time that made them has passed. The way the halo stars move sets them apart as clearly as their age. They do not travel in tidy circles within the plane, the way the Sun and its neighbors do. Instead, they fall along long, steep, plunging orbits that carry them high above the disk, down through it, and far below the other side. Each one behaves a little like a slow comet, but orbiting the entire galaxy rather than a single star, sweeping out and back across hundreds of millions of years. These steep orbits are the reason the halo is round rather than flat. The disk is flat because its stars all turn together in roughly the same plane, like water swirling in a bowl. The halo stars, by contrast, dive in from every angle, and the sum of all their tilted, plunging paths fills out a rough sphere. When one of them happens to be passing through our part of the galaxy, it stands out by its speed and its strange direction, a visitor from the old round cloud cutting across the orderly traffic of the disk. The halo is enormous, but it is very nearly empty. It holds only a small fraction of all the galaxy's stars, spread across a volume far larger than the disk. The stars within it are separated by far greater distances than the stars near the Sun. If a world existed around one of them, its night sky would be sparse, with only a scattering of faint stars, and below it, the bright disk of the galaxy would hang like a single luminous island in an otherwise dark sea. It is the loneliest part of the galaxy that still holds stars at all. Mapping such a faint and far-flung population is difficult, but the halo offers help in the form of certain stars that pulse. Some old stars brighten and dim on a steady, repeating beat, and the speed of that beat reveals how much light they truly give off. By comparing their true brightness to how faint they appear, their distances can be measured with real confidence. Scattered through the halo, these pulsing stars act as markers, letting astronomers trace the shape and reach of the old cloud out to great distances above and below the plane. What the markers reveal is that the stellar halo reaches much farther than the bright disk. While the disk spans about 100,000 light-years across, the old halo stars are found far beyond that, scattered through a roughly spherical region many times larger. The galaxy we see with the unaided eye, the bright flat wheel, sits at the center of a far greater sphere of faint old stars that almost no one ever notices. The halo also holds the fossil record of how the galaxy was assembled. The Milky Way did not form all at once as a finished spiral. It grew over billions of years, in part by drawing in smaller galaxies and pulling them apart. The stars of those swallowed galaxies did not vanish. They joined the halo, and many of them still move together in recognizable groups, tracing out the orbits of the galaxies they once belonged to. The old round cloud above and below the disk is, in part, a museum of the galaxy's own history. To rise into the halo is therefore to rise into the galaxy's memory. These are the first stars, still here, still circling, on orbits so slow and so patient that a single loop can take longer than the time since complex life appeared on Earth. They are in no hurry. They rise above the disk and fall back through it on cycles measured in hundreds of millions of years, having all the time the universe can offer. There is a stillness to the halo that suits this part of the night. The disk below is busy, making new stars, turning its arms, glowing with young light. The halo simply endures. It does not form new stars. It does not flare or change. It only holds its ancient population steady, drifting on long, quiet orbits through the dark, above and below. It is the calmest layer we have passed through so far, and the climb is only beginning. With the old stars understood as a round, sparse, ancient cloud surrounding the disk, the view can settle on the brightest things that cloud contains. Scattered through the halo, above and below the plane, are some of the most beautiful objects the galaxy holds, tight, glittering swarms of stars, older than almost anything else we can point to. They are the next stop on the way up. The metal-poor stars of the halo are in effect time capsules. A star locks into itself the mix of elements that filled the gas it formed from, and it carries that mix, almost unchanged, for its entire life. The halo stars formed when the galaxy was young and the heavier elements were still scarce, and so they carry that early scarcity within them today. To measure the composition of a halo star is to read a sample of the galaxy's gas as it was billions of years ago, preserved in starlight. Some of the oldest stars known anywhere belong to this old cloud. Among the halo's scattered suns are stars that appear to be nearly as old as the universe itself, formed in the first generations after the first stars of all. They are faint and unremarkable to look at, small and cool and long-lived, and yet they are among the most ancient objects we can point to. They have been shining steadily, above and below the plane, for almost the whole history of the cosmos. The halo is not a perfect sphere, but a slightly squashed and uneven one. It appears somewhat flattened, and its inner and outer regions seem to have somewhat different histories, as though the cloud were built in more than one stage. The inner part may hold the debris of a large early merger, while the outer part gathered more gradually from smaller pieces falling in over time. The shape of the old cloud, read carefully, is another record of how the galaxy came together. The sparseness of the halo is difficult to overstate. Where the disk near the Sun holds many stars within a modest reach, the same volume placed high in the halo might hold almost none. A traveler rising into the old cloud would find the stars growing steadily farther apart, until each one stood alone in a great stretch of dark, with the nearest neighbor far out of easy reach. The halo is spacious in a way the crowded disk never is, an open and ancient quiet surrounding the bright plane. Scattered through the old halo, above and below the disk, are some of the most beautiful structures the galaxy contains. They are called globular clusters, and each one is a dense, round swarm of stars, bound tightly together by its own gravity into a ball that has kept its shape for almost the entire age of the galaxy. There are roughly 150 of them known, and they do not belong to the disk. They orbit the galaxy as a whole, riding high above the plane and dropping back down through it on long, steep paths. A single globular cluster is a remarkable place. It can hold anywhere from tens of thousands to many hundreds of thousands of stars, all packed into a region only a few dozen light-years across. Toward the center of such a cluster, the stars crowd together far more closely than they do anywhere near the Sun. The distances between neighbors shrink from light-years to a fraction of that, and the whole core becomes a tight, glittering knot of suns held in a slow gravitational dance. The night sky of an imagined world inside a globular cluster would be like nothing we know. Thousands of stars would shine brightly enough to be seen at once, many of them far brighter than any star in our sky, and the nearest would blaze like small lamps hung close overhead. True darkness would never quite fall on such a world. There would always be enough starlight to cast soft shadows, a perpetual soft twilight made of the combined glow of 100,000 neighbors. These clusters are also among the oldest objects we can point to anywhere in the universe. They formed in the galaxy's earliest days, when it was still young and still assembling, and their stars have been shining gently ever since. The brightest, most massive stars that once lived among them burned out long ago, leaving behind a population of older, cooler, longer-lived suns. What remains is a steady, ancient light, glowing patiently above and below the plane for billions of years. Globular clusters belong firmly to the halo rather than the disk, and their orbits show it. They travel on steep, elongated paths that carry them tens of thousands of light-years above the plane, then draw them back down through the disk and out the far side. Over the long life of the galaxy, each cluster has made this plunging passage countless times, rising and falling through the bright sheet of stars without ever settling into it. They are visitors to the disk, never residents. Each passage through the disk is a small trial for a cluster. The gravity of the dense plane tugs at it, and over many crossings the outermost stars can be stripped away and left behind, trailing the cluster along its orbit. The tightest, densest clusters survive this again and again, holding their cores together through passage after passage. Looser ones slowly dissolve, giving up their stars to the halo over billions of years. The clusters we see today are, in part, the survivors, the ones strong enough to keep their shape. A few of the largest clusters may not be ordinary clusters at all. They are so big, so bright, and so unusual in the mix of stars they contain that they may be something else in disguise. The leading idea is that these giants are the surviving cores of small galaxies that the Milky Way swallowed long ago. The outer stars of those galaxies were stripped away over time, leaving only the dense central knot behind, which now orbits the Milky Way, looking much like a globular cluster, but carrying the history of a whole vanished galaxy. The clusters are spread all around the galaxy, but because they belong to the round halo rather than the flat disk, they are found in large numbers above and below the plane, in the very directions this night is exploring. To look toward a galactic pole is to look out past a scattering of these ancient swarms, each one a tight sphere of old suns, each one turning slowly on its long orbit through the dark. They are among the finest things the up and down axis holds. There is a particular beauty in watching, in the mind's eye, an entire cluster move. Picture a glittering sphere of 100,000 stars, hanging far above the bright disk. Slowly, over tens of millions of years, it falls toward the plane, passes through the sheet of younger stars, and rises out the other side, never pausing, never scattering, holding its round shape the whole way. It has done this since before the Earth existed, and it will go on doing it long after. These swarms tie the present galaxy to its deepest past. They formed in the first chapters, they survived everything since, and they still shine, steady and unhurried, in the quiet space above and below the disk. They ask nothing, and they change, almost not at all. They simply keep their slow orbits and their ancient light, a scattering of glittering spheres riding the halo through time. With the clusters understood as ancient, surviving swarms riding above and below the plane, the climb can lift to something larger still. The things waiting higher in the halo are no longer single clusters of stars, but whole galaxies, small companions, circling the Milky Way overhead and underfoot. The largest of the globular clusters is a remarkable object in its own right, holding several million stars in a single bound sphere, far more than a typical cluster. It is so large and so unusual in the mix of stars it contains that many suspect it is not a true cluster at all, but the stripped core of a small galaxy the Milky Way absorbed long ago. Whatever its origin, it rides the halo as a glittering ball of millions of suns, one of the finest sights the galaxy holds. The ages of the globular clusters once helped settle a fundamental question about the universe. Because the clusters are so old, measuring their ages sets a floor on the age of the galaxy and even of the cosmos itself. The universe must be at least as old as the oldest things within it, and the globular clusters are among the oldest things we can date. Their steady, ancient light gave one of the early measures of just how much time the universe has had. Within the crowded cores of these clusters, the close packing of stars produces gentle oddities. Stars pass near one another far more often than they do in open space, and now and then two will draw close enough to interact, producing stars that look younger than they should, refreshed by the encounter. These are quiet events by any cosmic measure, playing out over millions of years, but they show that even the most ancient swarms are not entirely frozen. Life of a slow kind continues in their crowded centers. It is worth lingering on how steady these swarms are. A globular cluster has held its rounded shape for almost the entire age of the galaxy, its stars orbiting the common center in a slow, balanced dance that neither collapses nor flies apart. Whole human histories, whole geological ages of the Earth pass in the time it takes such a cluster to change in any noticeable way. They are among the most enduring structures the galaxy contains, riding the halo above and below the plane with a patience measured in billions of years. Keep rising through the halo, and the structures encountered grow larger than any cluster. They become whole galaxies. The Milky Way does not float through space alone. It is the largest member of a small gathering of companion galaxies, most of them far smaller than itself, and they are scattered above and below the plane of the disk. These are the satellite galaxies, and they orbit the Milky Way much as moons orbit a planet, only on far grander and far slower paths, taking hundreds of millions or billions of years to complete a single loop. The two most famous companions hang low in the southern sky. To the unaided eye, from dark southern latitudes, they appear as two soft, glowing patches, looking almost like detached pieces of the Milky Way that have drifted away from the main band. They are not pieces of our galaxy, though. They are separate companion galaxies, each holding hundreds of millions to billions of stars, and they are among the nearest galaxies of their kind to us. They ride alongside the great disk, well off its plane, two bright neighbors keeping pace as the galaxy turns. These two companions are close enough that their structure can be studied in real detail. They are smaller and less orderly than the Milky Way, shaped more loosely, busy with their own star formation. A bridge and trailing streams of gas connect them, drawn out by the pull of each other and of the Milky Way. They are not quiet, finished objects, but living galaxies in their own right, lit with young stars and glowing clouds, slowly being reshaped by the giant they orbit. Beyond those two bright companions, the Milky Way is attended by dozens of much fainter dwarf galaxies. Most of them are so dim and so diffuse that they were found only by carefully counting their sparse stars against the crowded background of the sky. Each one is a complete galaxy in miniature, holding mostly old stars, bound to the Milky Way and slowly circling it through the halo. They are spread above and below the disk, small, faint clouds of ancient suns, easy to overlook, and yet genuinely galaxies in their own right. These dwarf companions are among the smallest and faintest galaxies known anywhere. Some hold only a few thousand stars, so few that they barely qualify as galaxies at all. Yet they hold together, circling the Milky Way for billions of years, kept whole by far more than their visible stars alone. They are quiet, old, and sparse, and they belong to the same round distribution as the halo stars and the globular clusters, filling the space above and below the disk rather than the plane. One of these companions is in the middle of a slow and gentle undoing. Its orbit carries it close to the Milky Way and through the crowded disk, and on each passage the galaxy's gravity pulls it further apart, stretching its stars into long streamers that trail along its path. It is still recognizable as a galaxy, but it is steadily giving itself up to the Milky Way, its stars joining the halo a little more with every loop. It is a companion, in the act of becoming part of the larger galaxy, slowly, across enormous spans of time. There is a quiet puzzle in the way these companions are arranged, and it can be held as gentle wonder rather than as any kind of conflict. Many of them do not seem to be scattered at random through the halo. A good number appear to lie within a broad, tilted sheet that cuts across the galaxy, as though the whole family had arranged itself along a plane of its own, set at an angle to the disk. Why so many companions should share such an arrangement is not fully understood. It is one of the honest, open questions about what surrounds us above and below. The companions also move, and over very long times their fates are bound up with the Milky Way's. Their orbits slowly decay, drawing them inward, and one by one, across billions of years, they are likely to be drawn in and absorbed, their stars added to the halo. The Milky Way has grown, in part, by gathering up companions like these throughout its history, and the ones we see now are simply the present members of a family that has always been changing. To picture the galaxy properly, then, is to picture not a lone spiral, but a spiral surrounded by a scattered company of smaller galaxies, riding above and below it through the dark. Two of them glow softly in the southern sky, bright enough to see. The rest are faint, old, and quiet, circling unseen. Together they make the Milky Way the head of a small flock, drifting through space as a loose group rather than alone. These companion galaxies belong to the same forgotten axis as everything else this night has found. They orbit through the halo, above and below the plane, in the directions we so rarely look. With the companions understood as a scattered family of galaxies circling our own, the view can turn to what happens when one of them comes too close and the Milky Way begins, gently, to pull it apart. The two bright companions in the southern sky are joined by a faint bridge of gas, drawn out between them by their mutual pull and by the larger galaxy they both orbit. This bridge, and the longer streamers that trail behind the pair, show that the companions are not isolated, but caught in a slow gravitational conversation with the Milky Way and with each other. They are being gently reshaped, their gas pulled into long arcs that reach across the southern sky. The fainter dwarf companions are strange in a particular way. They hold very few stars, yet they move as though they contain far more mass than those stars could account for. They appear to be bound together largely by unseen material, the same dark matter that fills the larger galaxy's halo. In a sense, these dwarfs are small clouds of dark matter that happen to hold a sprinkling of stars, the faintest and most delicate galaxies we know how to find. The count of known companions has grown steadily as our instruments have improved. Many of the faintest dwarfs were entirely unknown until careful searches picked their sparse stars out of the background, and it is likely that more remain to be found, too faint to have been noticed yet. The family of galaxies circling above and below the Milky Way is larger than it once seemed, and quieter, made up mostly of small, dim, old companions that reveal themselves only to a patient search. Seen together, the companions turn the Milky Way from a lone object into the head of a small flock. Two bright members glow in the southern sky, a scattering of faint ones circle unseen, and all of them move slowly through the halo above and below the disk. To picture the galaxy truly is to picture this quiet company drifting alongside it, a family of smaller galaxies kept close across billions of years, sharing the long journey through space. Some of the companion galaxies are not merely orbiting above and below the disk. They are being slowly unmade. When a small galaxy or a cluster passes close to the Milky Way, the larger galaxy's gravity does not pull on all of it equally. It pulls harder on the near side than the far side, and that difference stretches the visitor along its path. Over many passages, the stretched galaxy spills its stars out into a long, thin ribbon that follows its orbit. These ribbons are called stellar streams, and the halo above and below the disk is laced with them. A stellar stream is one of the gentlest forms of change the galaxy contains. Nothing in it is destroyed. The stars are simply drawn out of their small galaxy, one orbit at a time, and spread along a great arc that traces the path the galaxy has traveled. The result is a faint band of stars, thin and curving, wrapping part of the way around the Milky Way. Each stream is a record, written in starlight, of a small galaxy or cluster being slowly woven into the larger one. The grandest of these streams comes from the companion now being pulled apart on its passages through the disk. Its lost stars have wrapped more than once around the entire galaxy, forming an immense loop of starlight that arcs high above the plane, down through it, and far below the other side. A single shredded galaxy has been smeared into a band that nearly circles the Milky Way, a ribbon tens of thousands of light-years long, tracing the long, slow orbit of the dwarf that is dissolving into our own. Other, fainter streams thread the halo as well. Some are the unwound remains of globular clusters, drawn out into thin lines of stars by the same patient pull. Others come from dwarf galaxies that came too close long ago. Each stream keeps the memory of its origin in the way its stars move, all of them sharing a common path through the halo. Astronomers can pick these streams out by finding stars that move together in the same direction, even when the stars themselves are spread thinly across the sky. The streams we see forming today are only the most recent chapter of a process that has run for the galaxy's entire life. The Milky Way grew, in large part, by gathering smaller galaxies and pulling them apart, and the halo, above and below the disk, is the place where the evidence has collected. Much of the old material up there is the scattered debris of galaxies that were absorbed long ago, their stars now spread through the round halo, no longer recognizable as the galaxies they once were. One such ancient event left a particularly clear mark. Much of the inner halo, the old stars closest in above and below the disk, appears to be the scattered remains of a single substantial galaxy that the Milky Way absorbed in its youth. That galaxy is long gone as a separate object, torn apart billions of years ago. But its stars still move together in a recognizable way, sweeping out and back through the halo on similar paths, a hidden galaxy folded into our own. It is a ghost, present not as a shape in the sky, but as a pattern in the way certain stars move. This means the halo, for all its quiet, is in a real sense a graveyard, though a gentle one. It holds the remains of every galaxy the Milky Way has ever drawn in, their stars scattered above and below the plane, their streams still tracing the orbits they fell along. Nothing was destroyed. The stars all still shine. But the galaxies that once held them are gone, dissolved into the larger one, their material now part of the great round cloud surrounding the disk. There is a slowness to all of this that is worth holding on to. A galaxy does not come apart in a moment. It unwinds over billions of years, giving up its stars so gradually that, from the inside, nothing dramatic ever seems to happen. A star, torn from a dwarf galaxy, simply finds itself on a slightly different orbit, still shining, still moving through the dark, now part of a larger system. The violence of the words we use, torn, shredded, pulled apart, hides how gentle and how patient the process truly is. To look toward the halo, then, is to look at a place where lost galaxies are not erased, but rewoven. Their starlight still circles overhead and underfoot, traced into long, quiet ribbons, long after the galaxies themselves have ceased to exist as separate things. The streams are among the most delicate structures the up and down axis holds, and among the most telling, because they show the galaxy in the slow act of growing by gathering in its neighbors. With the streams understood as the gentle unwinding of swallowed galaxies, the climb can turn from starlight to something stranger. Standing over the very center of the galaxy, reaching far above and below the plane, are two of the largest single structures the Milky Way contains, and they are made not of stars, but of energy and hot gas. The stellar streams do more than record the past. They map the unseen present. As a stream of stars follows its long orbit through the halo, its exact path is shaped by the gravity it moves through, including the gravity of the dark matter that fills the region. By tracing the gentle bends and spreads of a stream, astronomers can feel out the shape of the invisible halo it travels within, using the ribbon of stars as a kind of probe. The streams let us map what gives off no light at all. The sun itself may be moving through the scattered remains of these old events. Among the stars near us are some that do not share the orderly motion of the disk, but instead move together in ways that mark them as visitors from the halo, perhaps the debris of a galaxy swallowed long ago. If so, then pieces of vanished galaxies pass quietly through our own neighborhood, mingling with the local stars, their different motion the only sign of where they came from. The process of gathering and unwinding continues today and will continue far into the future. The companion now being pulled apart will, over billions of years, give up the last of its stars to the halo, and other companions will follow as their orbits slowly decay. The Milky Way grows in this gentle way, not by sudden events, but by the slow, patient gathering of its neighbors, one ribbon of stars at a time, across spans of time longer than the age of the Earth. The gentleness of the streams is the part most worth holding on to. The words we use for them, torn and shredded and pulled apart, suggest violence, but from the inside, nothing dramatic ever happens. A star, drawn out of a dwarf galaxy, simply finds itself on a slightly altered path, still shining, still moving quietly through the dark, now part of a larger whole. The unwinding takes so long and proceeds so smoothly that it is less a tearing than a slow and patient joining. Not everything above and below the disk is made of stars. Reaching out from the very center of the galaxy, straight up and straight down out of the plane, are two of the largest single structures the Milky Way contains. They are enormous twin bubbles, swelling above and below the core in the shape of a great upright hourglass. For a long time, no one knew they were there, because they give off almost no ordinary light. Seen in the kinds of light the eye can detect, the space above the center looks unremarkable. Seen in higher energy light, two great lobes stand revealed, ballooning out of the core. The inner pair of these bubbles glows in gamma rays, the most energetic light there is. Each lobe reaches roughly 25,000 light-years above and below the plane, so that together they span a height comparable to a large fraction of the entire visible galaxy. They are filled with extremely fast-moving particles, the kind produced only by the most energetic events. To an instrument tuned to gamma rays, they are unmistakable, two smooth lobes, rising and falling away from the center in near-perfect symmetry. Around and beyond the gamma-ray lobes lies a second, even larger pair. These outer bubbles glow in X-rays rather than gamma rays, and they are filled with gas heated to extraordinary temperatures. They reach farther from the plane than the inner pair, swelling out into the halo above and below the center. Nested one set inside the other, the two pairs form a colossal double hourglass, standing upright through the disk, centered exactly on the core of the galaxy. The scale of these structures is difficult to hold in the mind. They are among the very largest things the Milky Way contains, and yet they are completely invisible to anyone looking up at the night sky, because they shine only in light our eyes cannot see. The bright band of the Milky Way passes right across the base of them, and no one watching that band would ever guess that two enormous lobes of energy and hot gas were standing silently above and below it, reaching far up into the dark. The bubbles are almost certainly the relic of a great release of energy from the galaxy's center in the relatively recent past. By the standards of a galaxy, recent means a few million years ago, the blink of an eye against the galaxy's full age. Something at the core poured an immense amount of energy up and down out of the plane, inflating the lobes we now see. They have been swelling outward ever since, slowly expanding into the halo, the cooling aftermath of an event long finished. The leading explanation points to the giant black hole that sits at the center of the galaxy. Most of the time, that black hole is quiet, drawing in very little and giving off little in return. But for a brief period in the past, it may have fed far more actively, and an actively feeding black hole drives tremendous outflows of energy along its axis, up and down, out of the surrounding disk. Such an outburst, lasting perhaps 100,000 years, could have inflated the great bubbles and then fallen silent again, leaving the lobes to drift outward on their own. There is a second possibility that may have played a part as well. The region around the center is one of the densest concentrations of gas in the galaxy, and from time to time, it can form stars in great numbers. A burst of star formation produces many massive stars that live briefly and end in powerful explosions, and the combined force of many such explosions can also drive gas up and out of the plane. Whether the bubbles came from the black hole, from a burst of star formation, or from some combination of the two, the result was the same. The center released a great breath of energy, and it rose above and below the plane. What makes the bubbles especially notable is their symmetry. They stand almost perfectly balanced above and below the disk, one lobe mirroring the other, the whole structure centered on the core. This is the same symmetry the whole night keeps returning to. Whatever the center did, it did equally in both directions, up and down, with no preference for one face of the galaxy over the other. The great hourglass is balanced because the galaxy itself has no true top or bottom for it to favor. The bubbles are also slow. They were inflated over 100,000 years and have been expanding for a few million more, timescales so long that, on any human scale, they are utterly motionless. They hang over the center, swelling so gradually that nothing about them would ever appear to move. They are a frozen breath, an event from the galaxy's recent past, still drifting outward in total silence, far above and below the bright plane where we live. To know they are there changes how the center looks, even though they cannot be seen. Above and below the brightest, busiest part of the galaxy stand two faint, luminous hourglasses, reaching tens of thousands of light years into the dark, glowing in light no eye can catch. They are the cooling memory of something the center did long ago, balanced perfectly between the two poles. With the great bubbles understood as the galaxy's frozen breath, the climb can turn to a gentler kind of motion, the slow rising and falling of gas that fills the space above and below the disk. The bubbles went unnoticed for so long, precisely because they hide from ordinary sight. They give off almost no visible light, and the bright band of the galaxy passes directly across their base, so that nothing in the everyday night sky hints at their presence. Only when the sky was mapped in the highest energy light did the two great lobes appear, standing over the center in near-perfect balance, structures larger than almost anything else in the galaxy, yet entirely invisible to the eye. The amount of energy stored in the bubbles is immense, far more than ordinary processes in the disk could supply. To inflate two lobes reaching tens of thousands of light years above and below the plane required a release of energy on a scale the galaxy reaches only rarely in its most active moments. The bubbles are a record of one such moment, a time when the quiet center briefly became one of the more energetic places in the galaxy and then fell still again. A faint haze of microwave light, gathered around the same region, appears to be part of the same event, another trace of the particles flung out when the bubbles were blown. Taken together, the gamma-ray lobes, the X-ray lobes, and the microwave haze tell a single story of a great release from the center, balanced above and below the plane. The very symmetry of the structures points to their origin, because only something at the center could have pushed equally in both directions at once. To stand, in imagination, far above the center and look back would be to see the two lobes rising on either side of the bright core, faint and enormous and perfectly balanced. They give off no light the eye could catch, and so the scene would appear, to ordinary sight, as simply the glowing center of the galaxy. Only to an instrument tuned to the highest energies would the great hourglass appear, two slow lobes of the galaxy's own breath, frozen in their long expansion, above and below the plane. The space above and below the disk is not still. Gas moves through it constantly, rising from the plane and falling back, in a slow circulation that astronomers have called the galactic fountain. The disk is where stars are born and where they die, and the deaths of the most massive stars are powerful events. Where many such stars live and die close together, their combined explosions blow great bubbles in the surrounding gas, and these bubbles can swell until they break out through the thin disk and vent hot gas upward, out of the plane and into the halo, above and below. This venting is the outward breath of the fountain. Hot gas, driven by the energy of many stellar deaths, rises out of the bright plane and into the quieter space above and below it. It carries with it the heavier elements that those stars made in their cores and scattered in their final explosions. In this way, the disk does not simply hold on to everything it makes. It breathes some of it upward, lifting enriched gas into the halo, where it spreads out and slowly begins to cool. The gas that rises does not escape forever. As it climbs into the halo and cools, it slows, stops, and begins to fall back toward the disk under the pull of the galaxy's gravity. It gathers into clouds as it falls, and those clouds rain gently back down onto the plane, returning the gas to the disk, where it can one day form new stars. This is the inward breath of the fountain. What the disk breathes out, it slowly draws back in a cycle that takes tens of millions of years to complete. Astronomers see this falling gas directly. Scattered above and below the disk are clouds moving at the wrong speeds to belong to the orderly rotation of the plane. They sweep inward and downward, clearly falling toward the disk rather than turning with it. These are called high-velocity clouds, and they are seen all across the sky above and below the galaxy. Some of them are returning fountain gas, cooled and falling back. Others appear to be fresh material, gas the galaxy is gathering from outside itself, drawn in to feed its ongoing star formation. The mix of returning and arriving gas matters for the galaxy's future. A galaxy that only spent its gas would eventually run out and stop forming stars. The Milky Way keeps going, in part because the space above and below the disk delivers a steady supply, some recycled through the fountain and some newly captured from beyond. The quiet rain of clouds from the halo is, in a real sense, what keeps the galaxy alive and forming new stars across billions of years. One of these falling clouds is large enough and close enough to follow in detail. It is an immense cloud of hydrogen, many thousands of light-years long, currently below the disk and arcing back toward it. It is moving quickly, and its path will bring it into the plane in roughly 30 million years. When it arrives, it is expected to strike the gas already there, compress it, and set off a wave of new star formation where it lands. It may even have passed through the disk once already and survived the crossing, looping back now for another encounter. This single cloud makes the whole process vivid. It is not a faint abstraction, but a specific, enormous object, a long streamer of gas falling slowly back toward the galaxy it came from, carrying within it the material for stars not yet born. It shows that the space above and below the disk is not empty waiting, but slow weather, gas rising and falling and arriving on timescales far longer than any human history, all of it eventually feeding the bright plane below. The fountain also helps explain why the disk stays as thin and as orderly as it does. Gas that is lifted out and gently returned settles back toward the midplane, drawn by the same gravity that keeps the disk flat. Over long times, this circulation smooths and replenishes the plane, keeping the thin, bright layer supplied with the cool gas it needs. The breathing of the galaxy is part of what maintains the calm, flat structure we live in. It is worth picturing the whole cycle as a single, slow breath. The disk breathes out through the bubbles and superbubbles blown by dying stars, lifting hot, enriched gas into the halo. The gas cools, gathers, and the disk breathes in again, drawing the clouds back down to make new stars. A single breath of this kind takes tens of millions of years, far slower than anything alive, and yet it never stops. The galaxy has been breathing this way for most of its life, and will go on doing so for ages to come. So the space above and below the disk holds a gentle, endless weather, gas drifting up, cooling, and raining softly back down onto the plane where new stars are made. It is one of the quietest and most patient processes the galaxy contains, and it ties the halo directly to the disk, the high, quiet space to the bright, busy plane. With the fountain understood as the slow breathing of the galaxy, the climb can turn to the rare things above and below that are not falling back, but leaving. The bubbles that break out of the disk to feed the fountain are themselves remarkable structures. Where many massive stars die close together, their combined explosions can clear out a region of the disk and drive a swelling shell of hot gas outward. When such a shell reaches the thin edge of the disk, it can burst through, opening a kind of chimney that vents hot gas up into the halo. Through these openings, the disk releases its heat and its enriched material into the space above and below. The gas that rises carries with it the heavier elements forged inside stars. Each generation of stars builds new elements in its core and scatters them in its death, and the fountain lifts some of this enriched material high into the halo before it settles back down. In this way, the heavier elements are mixed through the galaxy over time, carried up by the fountain, and rained back into the disk, slowly enriching the gas from which later stars and their planets form. This slow recycling is part of why the galaxy has been able to form stars steadily for so long. Rather than spending its gas all at once, the Milky Way lifts material out, lets it cool, and draws it back, stretching its supply across billions of years. The gentle weather above and below the disk is not incidental to the galaxy's life. It is part of what keeps the galaxy quietly productive, turning gas into stars at an unhurried, sustainable pace. There is a fitting rhythm in the idea of a galaxy that breathes. It draws material up through the deaths of its stars, holds it briefly in the halo above and below, and lets it settle back down to make new stars in turn. The breath is slow beyond any feeling, each cycle lasting tens of millions of years, and yet it has continued, steady and unbroken, for most of the life of the galaxy. The quiet space above and below the disk is where that long, slow breathing takes place. Almost everything above and below the disk is bound to the galaxy. The old halo stars, the globular clusters, the companion galaxies, the streams, the falling clouds of gas, all of them circle the Milky Way on long, patient orbits, rising and falling, but never escaping. They are held by the galaxy's gravity, and they will keep their slow loops for billions of years. But a rare few objects are doing something entirely different. They are leaving. Scattered through the halo are stars moving so fast that the galaxy can no longer hold them, climbing out of the plane and out of the galaxy for good. These are the fastest stars the Milky Way contains, and they are genuinely on their way out. Most stars move at a few tens of kilometers each second relative to their neighbors, fast by any ordinary measure, but far too slow to escape the galaxy. These rare runaways move several times faster, quickly enough to overcome the galaxy's pull entirely. Once a star reaches that speed and points outward, nothing will bring it back. It will cross the halo, leave the outermost reaches of the galaxy behind, and travel on into the space between galaxies. Most of these escaping stars were flung outward by the galaxy's own center. The giant black hole at the core is surrounded by a dense crowd of stars, and from time to time, a pair of stars orbiting each other wanders too close to it. When that happens, the encounter can capture one of the pair into a tight orbit around the black hole and hurl the other away at tremendous speed, like a stone released from a sling. The ejected star then races outward through the galaxy, often climbing steeply out of the plane, on a one-way path toward the halo and beyond. The journey of such a star is long and quiet. After its violent launch from the center, it simply coasts, crossing tens of thousands of light-years of the disk, and then the halo, above or below it, slowing only gradually as the galaxy's gravity pulls gently back. For most of its life, it travels through nearly empty space, a single sun moving steadily outward, carrying whatever planets it may have had along with it. Eventually, it passes the outer edges of the galaxy and continues into the dark between galaxies, where it will drift for the rest of its existence. Not every fast star comes from the center. Some are launched closer to home, when one star in a close pair ends its life in an explosion. The sudden loss of mass and the force of the blast can release the surviving companion like a slingshot, sending it off at high speed in whatever direction it happened to be moving. These runaway stars are usually not quite fast enough to leave the galaxy entirely, but they can still climb far above or below the plane, traveling through the halo on steep paths before falling back. The stars that do reach escape speed are among the only things in this whole night that are truly departing. Everything else above and below the disk is bound, circling, rising, and falling on closed orbits. These few alone are slipping away, crossing the halo for the last time, headed into the long emptiness between galaxies where they will never encounter another star closely again. They are the galaxy's most solitary travelers, and they are leaving it behind. It is worth setting their departure against the patient majority, because the contrast is the point. The halo is overwhelmingly a place of return. Stars and clusters and gas all rise out of the plane and fall back, again and again, held by gravity across enormous spans of time. The escaping stars break that pattern. They rise and do not return. In a galaxy defined by slow, endless orbits, they are the rare exceptions that simply keep going. Their leaving is gentle, despite the violence of their launch. From the perspective of the star itself, there is no drama. It moves through empty space at a steady speed, its surroundings thinning slowly as it climbs out of the galaxy. There is no boundary it crosses, no moment of departure, only the gradual fading of the galaxy behind it as it travels into the dark. Across millions of years, it simply finds itself farther and farther from the bright wheel it came from. These solitary stars give the up and down axis one more kind of motion. Most of what fills the space above and below the disk is circling or falling. A few things alone are rising and never coming back, carried out of the galaxy on paths that began with a single encounter at the center. They are a quiet reminder that even a galaxy as large as the Milky Way does not hold on to everything, and that now and then it lets one of its stars go on ahead into the wider universe. With the escaping stars understood as the galaxy's rare departures, the climb can rise past the last of the stars entirely, into a structure so faint and so large that it dwarfs the bright galaxy at its center. Surrounding the whole disk, reaching far above and below it, is an almost invisible atmosphere of gas, the true outer reach of the Milky Way. The speeds of the escaping stars are difficult to picture. They move quickly enough to cross the distance from the Sun to the galactic center, in far less time than an ordinary star would, fast enough that the galaxy's gravity, strong as it is, cannot turn them back. To reach such a speed requires an event of real force, and the most reliable source of that force is the crowded region around the central black hole, where close encounters can fling a star outward like a released sling. These stars are rare, only a small number known among the many billions in the galaxy, and finding them takes patient measurement of how stars move. A star betrays its great speed not by its appearance, but by its motion, and only by measuring that motion carefully can a true escaping star be told apart from the ordinary traffic of the disk. Each one found is a small confirmation of the violent encounters that take place, unseen, at the center of the galaxy. The fate of an escaping star is a long and solitary one. Having climbed out of the plane and crossed the halo, it enters the space between galaxies, where stars are almost impossibly far apart. They'll travel for the rest of its life without ever passing close to another star, carrying along whatever worlds it may hold, a single sun, adrift in the dark between galaxies. It is among the loneliest journeys the universe allows, and it begins with a single chance encounter at the crowded center. Set against the patient majority, the escaping stars make the rest of the halo seem all the more settled. Nearly everything above and below the disk is bound, rising and falling on closed orbits, returning again and again across the ages. These few alone break the pattern, climbing out and never coming back. In a galaxy defined by return, they are the rare departures, and their leaving quietly underlines how firmly everything else is held. Rise above the stars, above the clusters and the companion galaxies and the great bubbles, and the galaxy still is not finished. Surrounding the entire disk, reaching far above and far below it, is an enormous and nearly invisible halo of thin, hot gas. It is the true atmosphere of the galaxy, and it is larger than everything the eye can see. The bright disk, the old stellar halo, the clusters and companions, all of them sit inside this faint sphere of gas, which reaches several times farther out into space in every direction. This gas is extraordinarily thin, far more tenuous than the best vacuum that can be made on Earth. In any small volume, there is almost nothing there at all. But the volume it fills is so enormous that, taken all together, it adds up to a great deal of material. By some measures, this faint atmosphere may hold as much ordinary matter as all the stars of the galaxy combined, spread out across a sphere so large that the bright disk at its center looks small by comparison. The atmosphere is hot, heated to extreme temperatures by the energy of the galaxy's history, by the deaths of stars, and the outflows from the center and the slow infall of new material. At such temperatures, the gas glows only faintly, and only in high-energy light, which is why it went unnoticed for so long. It does not shine in any way the eye can catch. It is detectable only by careful study, by watching how it absorbs and scatters the light of more distant objects shining through it. This faint gas is also the galaxy's reservoir. The disk forms stars from cold, dense gas, and over time it would use up its supply if nothing replenished it. The surrounding atmosphere is where the new supply comes from. Slowly, across billions of years, the hot gas cools at its edges and settles inward, sinking toward the disk to feed the next generations of stars. The high-velocity clouds raining down onto the plane are, in part, this atmosphere condensing and falling inward, the outer reservoir delivering material to the bright layer where stars are made. The reach of this atmosphere is hard to overstate. It extends so far above and below the disk that it begins to approach the atmospheres of other galaxies. Our nearest large neighbor, a great spiral much like our own, has an enormous gaseous halo of its own, reaching far out into the space between the two galaxies. The two atmospheres reach so far toward each other across that gap that they may nearly meet somewhere in the middle. In a real sense, the outer edge of what lies above and below the Milky Way is not a sharp boundary at all, but a slow thinning that fades until it brushes against the next galaxy's faint outer reaches. This means the galaxy has no true edge. We are used to thinking of objects as having surfaces, clear boundaries where they stop and the outside begins. The Milky Way has nothing of the kind. Rising up out of the disk, a point of view would pass through the stars, then the sparse halo stars, then the thin hot gas, with the gas simply growing fainter and fainter without ever quite ending. The galaxy does not stop. It fades, reaching outward until it meets its neighbors. Beyond even the gas lies something larger still, though it gives off no light at all. Surrounding the whole galaxy, reaching farther than the visible disk and farther than the hot atmosphere, is an enormous halo of dark matter, known not by any glow, but by the pull it exerts. It is this unseen halo that holds the galaxy together, that keeps the disk turning at the speed it does, and binds the clusters and companions to their long orbits. It is roughly spherical, like the stellar halo, filling the space above and below the disk with a presence felt only through gravity. The dark halo is the largest part of the galaxy by far, and the most quiet. It does not shine. It does not form structures we can see. It simply surrounds everything and holds it in place. The bright disk, with all its stars and arms and glowing gas, is a small luminous thing suspended at the center of this far greater unseen sphere. When we ask what sits above and below the galaxy, the most far-reaching answer is this. Above and below, more than anything else, lies the great, invisible halo that the whole visible galaxy floats within. So the galaxy fades outward, in stages, rather than ending at any edge. First the stars, then the sparse old halo stars, then the thin hot atmosphere of gas, then the still larger unseen halo of dark matter, each one reaching farther above and below the plane than the last. There is no wall, no final boundary, only a slow and steady thinning that eventually brushes against the next galaxy. The Milky Way has no skin. It only reaches, ever more faintly, into the dark. With the invisible atmosphere and the dark halo understood as the galaxy's true outer reach, the climb can finally pass through the last of it and look outward, beyond the galaxy entirely, to the quiet architecture of the universe that waits above and below in the open space between galaxies. The faint atmosphere of the galaxy is thought to hold a large share of the ordinary matter the galaxy contains, matter that is not in stars at all. For a long time, the accounting did not add up. The stars and visible gas seemed to fall short of what a galaxy like ours should hold. Much of the missing material appears to be here, spread thinly through the great gaseous halo above and below the disk, too faint to have been counted until careful study revealed it. This gas is found not by its own light, but by the way it dims the light of things behind it. When the bright light of a distant object passes through the halo on its way to us, the gas leaves faint fingerprints on that light, absorbing particular colors in particular ways. By reading those fingerprints, astronomers can measure the gas that gives off no glow of its own, mapping the faint atmosphere by the shadows it casts on more distant light. The outer boundary of the galaxy, in any meaningful sense, is set not by the stars, but by this gas and the dark halo beyond it. There is a radius within which the galaxy holds sway over the material around it, far beyond the visible disk, and the gaseous halo reaches out toward it. To ask how far the galaxy extends above and below is really to ask how far this faint reach continues, and the answer is far enough that it begins to touch the reach of our neighbors. The picture this leaves is of a galaxy without a surface, fading rather than ending. Rising out of the plane, one passes the stars, then the sparse old stars, then the thin hot gas, then the unseen halo, each fainter than the last, none of them stopping at any clear line. The galaxy simply reaches outward, more and more faintly, until its reach brushes against the reach of its neighbors. Above and below, in the end, the Milky Way does not stop. It only grows quieter, and quieter still, into the dark. Pass through the last of the galaxy's faint atmosphere, and the climb arrives at last in open space. We are truly above and below the Milky Way now, out beyond the stars and the gas, in the quiet between galaxies. From here, the disk would no longer surround a point of view but hang in the dark as a single object, a glowing wheel of light seen from outside, with its faint halo of clusters and companions scattered softly around it. It would look small and complete and very far away. The view from out here is the calmest the whole night offers. The bright, busy plane, with all its young stars and turning arms, becomes one luminous pinwheel suspended in the dark. The old halo wraps it in a faint, round glow. The companion galaxies hang nearby as small, soft patches. The whole structure that took so long to climb out of is reduced from this distance to a single, quiet light among the others, turning slowly in space. The Milky Way does not float out here alone, though. It belongs to a small gathering of galaxies, bound together by gravity into a loose group. Our own galaxy and one other great spiral dominate the group, and around them circle a few dozen smaller galaxies, including the companions we have already met. This group drifts through space as a unit, its members slowly orbiting one another, held together while the wider universe expands around them. It is the galaxy's immediate neighborhood, the next layer outward from the halo. Above and below that local group, the universe organizes itself into a great and quiet architecture. Galaxies are not scattered evenly through space. They gather along long strands and sheets, strung through the dark like a faint web, and between those strands lie enormous regions that are nearly empty. The bright places, where galaxies cluster along the strands, surround the dark places, where almost nothing is. On the largest scale, the universe looks like a network of luminous filaments wrapped around immense hollow spaces. Our own galaxy sits within this web, near the edge of one of its great empty regions. In one direction, out of the plane, lies an enormous, nearly vacant stretch of space, a place where galaxies are remarkably few. The Milky Way drifts slowly along the border of this emptiness, gently pushed away from it, as though the great void were quietly expanding and nudging its neighbors outward. We sit on the shore of one of the universe's large hollows, drifting along its edge across spans of time beyond imagining. Looking out through the galactic poles, our sight passes through the clearest windows the galaxy offers and reaches this large-scale structure directly. The long exposure images aimed near the poles, gathering faint galaxies by the thousands, are in fact sampling the cosmic web, catching the strands and the hollows as they appear at greater and greater distances. The forgotten up and down axis turns out to be our best line of sight onto the largest patterns the universe contains. There is a humbling scale to this outermost view, but it is a gentle humbling rather than a frightening one. The galaxy that took the whole night to climb out of is one light among uncountable others, strung along a web that stretches as far as any instrument can see. And yet there is order in it, a soft architecture of strands and hollows, calm and slow and unchanging on any timescale we could feel. The universe at its largest is not chaos. It is a quiet, patient network, and our galaxy is one small, bright knot within it. From this distance, the question that began the night takes on its widest meaning. Above and below the Milky Way, far past its own halo, lies the rest of the universe, arranged in its great web of light and emptiness. The same two directions that point out of our crowded disk point, eventually, toward everything else there is. To look up out of the plane is to look toward the whole cosmos, laid out in the dark. Having reached the widest view, the night can begin its return. The climb is complete. From here, the only way is back down, toward the bright plane, toward the small, warm world we set out from. And on the way back, there is one last piece of the story to tell, the most personal of all, because it concerns not the galaxy's structures, but our own slow motion through them. The local group of galaxies is a quiet neighborhood by cosmic standards, held together while the wider universe expands around it. Its two great spirals and their scattered dwarfs orbit one another slowly, bound by gravity into a single system that moves through space as a unit. Within the group, the galaxies are close enough to feel one another's pull and to slowly draw together, even as everything beyond the group recedes into the distance. The strands of the cosmic web are made of countless galaxies and groups like ours, strung along filaments that can stretch for enormous distances. Where the strands cross, galaxies gather most thickly, and between the strands lie the hollows, regions so empty that a galaxy within one would see very few neighbors at all. The pattern repeats on scales almost beyond comprehension, a network of light wrapped around darkness, filling the universe as far as any instrument can reach. From the calm of this outermost view, the whole climb falls into place. We began in the crowded plane, rose through the thinning layers of the disk, past the old stars and the swarms and the companions, crossed the bubbles and the falling gas, moved past the faint atmosphere, and arrived here, in the open space where the galaxy is one light among many. The directions above and below, which seem to hold nothing, have led all the way out to the largest patterns there are. There is a calm that comes with this widest view, rather than any sense of being lost. The galaxy that took the whole night to climb out of becomes one quiet light among many, strung along a soft network of strands and hollows that fills the universe in every direction. The pattern is orderly and slow, unchanging on any timescale we could feel, and our own galaxy holds a settled place within it, drifting gently along the edge of one of the great empty regions. From here, the return can begin. Having reached the open space beyond the galaxy and seen the cosmic web laid out in the dark, the only way left is back down, toward the bright plane and the small, warm world the night set out from. The descent retraces the climb in reverse, past the faint atmosphere, the falling gas, the swarms, and the old stars, back toward the thin, bright layer where the light gathers and where we belong. There is one more piece to the story of above and below, and it is the closest to home. We are not fixed in the plane of the galaxy. As the Sun carries its planets in their long orbit around the galactic center, it also moves gently up and down through the disk, rising above the central plane, slowing, falling back through it, dropping below, and rising again. We do not simply circle the galaxy. We bob, slowly, through its bright midline, over and over for as long as the Sun has existed. The motion is gentle and small compared with the galaxy, but it is entirely real. The Sun rises at most a few hundred light-years above the central plane before the gravity of the disk draws it back down. Then it falls through the midline, descends a similar distance below, slows, and is drawn back up again. Each full cycle of this rising and falling takes somewhere in the range of 60 to 70 million years, a rhythm far longer than any creature could feel, playing out quietly beneath the more obvious motion of our orbit around the center. The cause of this bobbing is the disk itself. The flat sheet of stars and gas has its own gravity, and that gravity always pulls toward the midplane. When the sun drifts above the plane, the mass of the disk below pulls it gently back down. When it overshoots and drops below, the mass of the disk above pulls it gently back up. The result is a slow oscillation, the sun swinging back and forth through the plane like a weight on a long, soft spring, never settling, always drawn toward the middle. At this moment, the sun sits just slightly above the exact midplane and is drifting slowly upward. We are, very gently, on the rising part of the cycle, moving by small degrees toward the space above the disk. The motion is far too slow to notice in any lifetime, or in all of recorded history put together, but it is real and it is steady. Right now, imperceptibly, the whole solar system is climbing, carried upward through the bright plane on the longest of rhythms. It is worth saying clearly, for anyone drifting towards sleep, that this motion is entirely gentle and poses no danger at all. The plane is not a barrier or a surface. It is simply a region where the stars and gas are a little more concentrated, and crossing it is smooth and uneventful. The sun has made this slow vertical passage many dozens of times already, carrying the Earth and everything on it safely through, and it will make it many dozens more. There is nothing to brace against and nothing to fear in the crossing. The distances involved keep the motion safe. Even at its highest, the sun rises only a few hundred light-years above a plane that is itself hundreds of light-years thick and 100,000 light-years across. We never travel far from the midline in proportion to the size of the disk. We simply drift up a little and down a little, staying always within the broad, bright layer where we belong, rocked slowly back and forth across tens of millions of years. This slow bobbing ties us personally to the whole subject of the night. The space above and below the disk is not somewhere distant and separate from us. We move through it ourselves, gently, all the time. We have risen above the plane and fallen below it again and again over the life of the solar system, carrying our small world through the same up and down axis that holds the halo stars and the clusters and the great bubbles. We are not observers of this axis from outside. We ride it. There is something quieting in the thought of being carried this way. The whole solar system, the sun and all its planets, is borne slowly up and down through the bright plane on a tide far longer and far gentler than any other we know. It asks nothing of us. We do not have to do anything to be carried. We simply ride the slow swell, up through the plane and down again, held the entire time within the broad, bright layer of the galaxy, safe and unhurried across spans of time beyond counting. So the most personal answer to the night's question is also the simplest. What sits above and below the Milky Way includes us, gently rising and falling through its plane right now, on a rhythm tens of millions of years long. We are part of the slow vertical motion of the galaxy, carried along with everything else, rocked softly through the bright middle. With our own bobbing understood as part of the larger pattern, the night can settle into its final thought, the quiet truth the whole climb has been circling. The motion is best pictured as a weight on a long, gentle spring. The disk pulls the sun toward the midplane from whichever side it has wandered to, always drawing it back toward the center, never quite letting it settle. So the sun swings slowly through the plane and out the other side, slows and swings back in an oscillation that never ends as long as the disk holds its shape. It is the gentlest kind of motion, a slow and steady rocking that has no jolt anywhere in it. Our current place in this rhythm is a quiet one. The Sun sits just above the midplane, having crossed it not long ago by the galaxy's slow clock, and it is drifting gently upward toward the space above the disk. We are near the middle of the swing rather than at its top or bottom, moving steadily but not far, carried upward by small degrees on a climb that will take millions of years to reach its modest height before turning gently back. It is the smallness and slowness of this motion that makes it safe. We never leave the broad, bright layer of the galaxy. We only drift a little above its center and a little below, again and again. The crossings of the plane are smooth and uneventful, and the Earth has been carried through them many times already without harm. There is nothing in the motion to brace against, only a slow and endless rocking that has held us safely for the whole life of the world. The thought of being carried this way, gently and without effort, is a fitting one for the close of the night. We do nothing to ride the slow swell. We are simply borne along, up through the plane and down again, held the entire time within the broad, bright layer of the galaxy. The motion has rocked the Earth across its whole long history and will go on rocking it for ages more, a tide so slow and so steady that nothing alive has ever felt it, and yet it carries us all the same. Having risen all the way out of the galaxy and begun the slow return, the night can finally answer its own question, and notice that the answer is very nearly the same in both directions. Above the disk lie the old halo stars, the glittering globular clusters, the companion galaxies, the long ribbons of shredded starlight, the great bubbles standing over the center, the slow rain of falling gas, the rare escaping stars, the faint enormous atmosphere, and beyond it all, the wider universe. Below the disk lies very nearly the same, mirrored. The galaxy is built evenly around its bright middle, and there is no real difference between its two faces. This is the quiet truth the title was pointing toward from the start. The Milky Way has no top and no bottom. It floats in space with no up and no down of its own, the same in every direction away from its disk. We give the two poles names for convenience, north and south. But the galaxy itself does not lean either way. Everything above us has its mirror below us, and the whole structure simply turns, slowly, in the dark, the same on both sides. There is a quiet restfulness in this symmetry, once it settles in. We are used to a world with a floor beneath us and a sky above, with a clear direction to fall and a clear direction to rise. The galaxy has neither. There is no edge to fall off, no floor to fall toward, no ceiling pressing down from above. There is only the bright plane holding us in its middle, and the same quiet space reaching away in both directions, balanced and open and calm. We live in the one layer where the light is, the thin bright sheet crowded with stars, held there gently by the gravity of the disk. Above and below us, in the directions we so rarely look, the galaxy keeps its oldest and largest and quietest things, arranged in near-perfect balance. We are suspended in the middle of all of it, rocked slowly up and down through the plane, carried along as the whole galaxy turns. Nothing above or below asks anything of us. The halo stars circle on their long, slow orbits. The clusters rise and fall through the plane. The bubbles drift outward over the center. The gas breathes slowly up and down, and the great dark halo holds it all in place. All of it moves on rhythms far longer than any life, patient and indifferent and steady. It was there long before us, and it will be there long after, turning quietly in the dark, whether or not anyone is watching. The mirror between above and below runs through everything the night has found. The old stars circle on both sides of the plane. The clusters rise and fall through it equally. The companions and streams fill the halo all around. The great bubbles stand balanced over the center. The faint atmosphere reaches outward in every direction at once. Nowhere does the galaxy favor one face over the other. It is built evenly, top to bottom, around the bright layer where we live. To live without an edge, without a floor or a ceiling, turns out to be a gentle thing rather than a frightening one. There is nowhere to fall because there is no down to fall toward. There is nothing pressing from above because there is no ceiling overhead. There is only the bright plane holding us in its middle, and the same calm space reaching away in both directions, balanced and open and quiet, the same whichever way we choose to look. It helps, at the close, to hold the whole structure in a single image. Picture the galaxy from far away, a bright, flat wheel of light, turning slowly in the dark. Around it, above and below in equal measure, hangs the round faint glow of the old halo, dotted with glittering swarms and small companion galaxies, threaded with ribbons of starlight, crowned over its center by two balanced lobes, and wrapped in a faint atmosphere of gas that fades softly into the space between galaxies. That is the answer to the night's question, gathered into one quiet picture, the same on every side. So the night ends where it began, with the gaze tipped gently out of the plane, but now the dark above and below is no longer empty. It holds old stars and glittering swarms, companion galaxies and ribbons of starlight, great balanced bubbles and slow-falling rain, a faint, enormous atmosphere, and beyond it all the quiet architecture of the universe. The forgotten axis turned out to hold the oldest and largest and calmest things the galaxy keeps, arranged in near-perfect balance on both sides of the bright plane. There is nothing in any of it that asks anything of us tonight. It moves on rhythms far longer than any life, patient and slow and balanced, the same above as below. It was there long before us and will be there long after, turning quietly in the dark, whether or not anyone is watching. To know it is there, above and below, is enough, and it can be set down now, gently, like everything else, as the night comes to its close. And so we let the galaxy float where it has always floated, with no top and no bottom, the same above as below, holding us gently in its bright middle, while everything around it turns slowly through the dark. There is no edge to fall from here, and nothing you need to carry. Let the bright band soften. Let your breathing slow. Let yourself be rocked, gently, up through the plane and down again, held safely in the one warm layer where the light is. Sleep well, and good night.